So my name is Fedor, and I'm from Facebook. I'm presenting the paper Rosetta large-scale system for text detection and recognition in images. This work is done in collaboration with Search and Machine Learning Organization at Facebook. The other two co-authors are Albert and Vish. So let's start with the definition. What is optical character recognition? Let's say you have an image. It has a text printed, somehow painted on the image, and you want to extract this text and put it to a machine and coded form. So when it comes to the social networks, in these days, social networks like Facebook or Instagram, many people deploy images. Many images do have tags, so it's very important to understand the content of these images so we can serve recommendation or search applications for these images. And another problem that arises is there are more or less billions of images deployed every day, so how do you process this in a very scalable form? So the solution we developed on Facebook is a two-step process. So in the first step, we take the image, we detect the bounding boxes across every word, and then run recognition model based on the CTC laws to recognize the characters from the word. The benefits of the two-step process is because we can deploy the models independently and we can develop them independently. Now let's take a look at the example. So let's say you have an image and you have a question if penguins can really fly. So we can firstly detect the bounding boxes around every word in the image. We use fast RCNN to do that. And then for each of the bounding box around every word, we run a ResNet 18 model with CTC laws to recognize characters from the word. That was the overall process. Now let's go deeper into what's the models behind every step. As I mentioned, we use fast RCNN model to detect bounding boxes. It uses a convolutional body with shuffle-net, so we can run faster inference. And some of the lessons that we learned is it's very important to actually make this model faster. And I will show more details on how we do that in the experimental section. And another lesson that we learned is if we train with F1 measure, which was initial loss metric for Cocotax dataset that we use in experimentation, actually the training process is not very stable because F1 measure is just selected with a certain threshold on the precision recall curve. And once you initialize the weights of the neural network randomly, then every time you get something different at the end. So what we did is we replaced it with mean average precision, which is just the area under the curve, and that helps to stabilize the training. That's one of the learnings that we had. And as of recently, Cocotax also moved to MAP. Now let's talk about the recognition model. So we use ResNet 18 architecture here, and after we do all the transformations, we get to the feature map of alphabet size to the length of the word, to the width of the word, and we use a CTC loss to train this network. If you think about CTC loss, what it does is it uses dynamic programming to feed from the input sequence of the word to the ground truth that happens during training. And important aspect of it is you can, on each of the feature columns, you can have the same character in the output. So it means that you have a longer sequence that you need to dynamically, using dynamic programming to feed to a shorter sequence. It also learns to output so how do you solve the problem of deduping this? It also learns to output the separation symbol between the characters. And then as a post-processing step, you more or less dedupe the characters to get the final result. And in the inference, we use a greedy algorithm where at every step on the feature column, we greedily output the symbol that is most likely. One aspect of the CTC laws is that it's actually very hard to train. It's a known issue in the research community. So what people usually do, they train a classification network and pre-train the classification network and then fine-tune CTC layer, more or less softmax layer on top of that. While we thought this is a hacky procedure, so we decided to say, okay, how can we train it actually end-to-end? And we used curriculum learning. So when you, for example, learn how to read, you start with very simple stuff and then you gradually increase your reading skills. So we do the same with a model where we start with smaller learning rates and we also start with shorter words, let's say 3-character words. We filter out the training set, and in every step in the warm-up stage, pre-training stage, we increase the complexity of the examples, and let's say we go to 4-character words, 5-character words, and also increase the learning rate. And then in the main training procedure, we also continue doing that. We increase the length of the words, and also once the loss stabilizes, we decrease the learning rate, as usual. There are several interesting steps that we did to normalize the images for recognition. So firstly, all the images are normalized to 32 by 128 for pixels during the training time. So that helps us to do effective training. And testing time and the inference time, we resize it to the 32 to the length of the image. So it means that in the testing time, we can recognize any number of characters. And another improvement that we did is we stretched the images by 1.2. You might think, why is that? And one intuition we have is when you do convolutions, it actually compresses the image. If you think, let's say you take a character and you try to squash it, so you would not be able to read it, but if you make it longer, let's say character A, you still can read it. So that's the intuition we have, is that when we make the image longer, you can actually improve results. And in terms of how it is processed, images are deployed to Facebook through, so let's say, a mobile application, a front-end server. They get put to the processing queue, then Rosetta, that's how we call the system, it pulls from the queue, it does localization of the words and then recognition of every word, and then we put it to a database from where applications like search or any type of recommendation systems in Facebook can use it. So we used 3 data sets to train our models. First data set is open source data set called Coco Text. It has around 60,000 images. We also use synthetic data set. For OCR, it's a wonderful world. So you take the image, you can actually generate thousands and thousands of data by just randomly selecting font and words from the dictionary, then selecting random font, location, rotation, any type of distortions, and special symbols, URLs, whatever it is, and print it on the image and then use it as a training data. So we generated about 400,000 of synthetic images like that. And we also collected some of the human-rated data specifically for applications that we targeted. In terms of the measurements, I already said that for detection model, we have used mean average precision. For a recognition model, we have used accuracy, and also Levenstein distance to measure the character-wise distance between the prediction and ground truths. Let's look into some of the evaluations. So for detection model, we tried different architectures, so we ended up conversion to ShuffleNet. It's faster for the runtime, and it gives reasonable quality results to what we expected. We also experimented with top-end parameters, and we ended up selecting 100 for efficiency reasons. It's a top 100 candidates from the image to retrieve the text, top 100 candidates from image to retrieve text from them. And we experimented with different suppression methods for the candidates from the detection, and linear soft NMS worked the best. For detection, we also experimented with different data sets. So how we did, we trained on synthetic, then fine-tuned on COCO, and then fine-tuned on human-rated data. Why is it important? Because if you think about distribution of images, synthetic would work on something like memes, where people take some initial photo and they printed text on that. Synthetic would probably solve that problem really well. If we start to look into the images in the natural circumstances, let's say you take a photo on the street, then COCO text is going to help, and there are certain interesting applications in Facebook that required fine-tuning on human-rated data specifically for those applications to improve the quality. As for recognition, we compared it with one of the previous works in the field. I refer this model as CHAR model here. It's Joderberg's. It's one of the models from Joderberg's papers. So what it does, it's a classification model which can detect, let's say, 23 characters, where for every character you have a classification head predicting one of the characters of the alphabet. And using CTC trained model actually improves somewhat around 6%, and then using data sets specific to the domain improves quite a bit on top of that. And other things we tried to train, let's say, with uppercase or lowercase, and actually doesn't really change the accuracy of the model, but it does help to recognize words with the different cases, so we still use it. And another problem, if you think about the overall process, so you have detection and then recognition, so actually it's end-to-end performance depends on the both sides. So how can you improve and how can you fix errors from the detection? And what we did is that we took the ground truth boxes before feeding them to train into recognition, and we jitter them, move them around a little bit to add the noise such that it can emulate the errors from the detection phase. And it improved the quality, overall quality of the system. And if I draw the summary, so you can remember what is important from this work is firstly, use MAP for training your detection models for text. And it's important to use different data sets for achieving the performance you want on the applications you want. Random jittering does help to solve detection problems. In our case, we used faster CNN, and to improve on top of that on the recognition phase. It's very important to have non-dictionary prediction recognition model so that you can actually extract any characters, any alphabet, and it can work more or less anywhere. And to train in the CTC loss, you really need to make sure you either pre-train with some other classification model or use techniques that we describe in this paper to make it stable. And upper lowercase didn't help to us, but it's a good thing to have in your recognition model. As of now, this model is deployed, this system is deployed to Facebook. We process hundreds of millions of images deployed every day and have happy customers like search in memes on Facebook and have fun. Questions, please.